All right, we're going to be talking about a very important concept, intermolecular forces. This is something that's really going to connect not just to this current unit, but also to our next couple of units. First off, a couple things to remember. Ionic bonding, this is between a metal and a nonmetal. This is a transfer of electrons. This is when positive and negative ions are formed that attract each other. Molecules, which are a type of covalently bonded substance, can be considered nonpolar or polar. We just did this in our last concept. Nonpolar molecules have equal charge distribution, and polar molecules have unequal charge distribution. We talked a little bit about how polar molecules can also be called dipoles, which you'll see in this presentation as well. So, intermolecular forces, these occur between separate molecules. That's where the inter comes from. We're talking about between two separate molecules. These are attractions between the molecules. None of these are types of bonds. These are just simply attractions between them. So even though a molecule is a complete unit, they can attract one another. So we have three types we're going to focus on. The first one is our weakest type of intermolecular force, or IMF. It's called van der Waals forces. Commonly you'll see it as London dispersion forces. These always take place between non-polar molecules. So you want to definitely memorize and know that London dispersion forces have to do with non-polar molecules. These are very, again, weak. They become weak dipoles, these non-polar molecules, for short periods of time, resulting in a weak force called our London dispersion forces. So even though they're nonpolar, as they approach each other, they affect each other's electron densities and become, again, weak dipoles for a very short period of time. So the strength of our van der Waals or London dispersion force increases as the particle size increases. So as the molecule gets bigger, the strength of the van der Waals force also increases. So again, forces increase as particle size increase. So if we look at our halogen groups, iodine is the largest out of that group 17, fluorine being the smallest. So why is iodine a solid, bromine a liquid, and chlorine and fluorine a gas? Well, it actually has to do with our intermolecular forces. Iodine is larger, so because we have a larger molecule, we have a stronger intermolecular attraction, or IMF, between the molecules. So because there's a stronger attraction, they're held closely together, that the phase at STP results in a solid. However, Cl2 is smaller, so again, smaller the size, the smaller the attractive force, so the weaker the attraction, or IMF, between molecules of Cl2. These particles are then, because of the weak attraction or pull between them, these are able to be farther apart from each other, forming a gas. So phases, for some of the things that we'll be talking about, have to do with these IMFs, or these attractive forces between them. All right, our kind of medium strength IMF is called a dipole-dipole attraction. These occur between polar molecules, and they attract each other due to their partial charges. So remember in our last concept when we talked about molecular polarity and how we have some molecules, polar molecules, that have an uneven distribution of charges? These are those partial charges. So remember, this results from a difference in electronegativities and also having an asymmetrical shape. So here we can see that there's an uneven charge distribution. We have a partial negative charge here. So those develop our partial charges, which can then attract other molecules. So here we have HCl, hydrogen. Again, this is a covalent bond between the atoms, an actual bond, which causes a partial positive on our hydrogen, a partial negative on our chlorine. That partial negative on chlorine attracts the partial positive on the hydrogen of another molecule. So while we have a covalent bond between hydrogen and chlorine within a molecule, between them we have a dipole-dipole IMF. And again, just like before, the bigger the molecule, the greater the attractive force between molecules. Finally, hydrogen bonding, and put a big star in your notes next to hydrogen bonding. You absolutely have to know and understand hydrogen bonding. This is an extremely strong dipole-dipole attraction that occurs between molecules that have a hydrogen bonded to fluorine, oxygen, or nitrogen. The three common examples that you should absolutely know for hydrogen bonding are NH3, H2O, and then hydrogen fluoride, HF. So a hydrogen bond, just like our other IMFs, occur between two separate molecules. So in this case we have water, H2O. The partial negative charge on oxygen is going to attract the partial positive on the accompanying hydrogen of a separate molecule. So a strong attractive force between means you have a very high boiling point. So we would expect normally that water would actually have a lower boiling point than H2S, and sulfur is just in the same group, so we would expect similar properties or a similar trend to occur. However, we find that unlike our expectations, H2O actually has a higher boiling point because of these extremely strong IMFs, or hydrogen bonding IMFs. So here's kind of a visual graph. Okay, we would expect this trend for group 16 that oxygen would be lower than H2S, so H2O would we expect to be lower. However, as you can see, these three have kind of gone against the trend in our expectations by having these higher, much higher boiling points or temperatures relating to their boiling points. And again, this has to do with the strong IMFs between molecules in a sample of those compounds. All right, now we're going to talk briefly about something called molecule ion attractions. So this occurs that ions in ionic compounds such as NaCl dissolve in water. This is because ions are attracted to the positive and negative ends of the water molecule. So this is referred to as hydration. Basically, the water destroys and tears apart the ionic crystal. So you're going to see here the larger circles representing oxygen. Remember, oxygen takes on a partial negative charge. So this positive ion from our ionic crystal, we can then see that the negative part of water, the oxygen, all orientate and point themselves towards the positive ion of the ionic crystal. Same thing over here. We can see all the hydrogens, which take on a partial positive charge, orientate themselves around the negative ion. And we'll be drawing this tomorrow in class as well and talking more about it. So a couple of things that I think you should kind of start to think about is how does this connect to our next unit on phases? Well, the weaker the IMF, the lower the melting and boiling point. So that's because it takes less energy to overcome weak IMFs. However, something that has a really strong IMF, like a hydrogen bond, has the highest melting and boiling points. It means it takes much more energy to overcome stronger IMFs and break molecules apart from each other. So that's one thing to kind of keep in mind as we come back and start on phases. Now, how does this connect to our future unit on solubility? This is a very common phrase you'll hear basically when we come back after our February break and we work on solubility, is that like dissolves like. Nonpolar molecules will dissolve in nonpolar solvents. Polar molecules will dissolve in polar solvents, and then ionic compounds will dissolve in polar molecular solvents. They're similar enough to be able to dissolve each other. All right, so you can go ahead and write your summary or go ahead and take the Edmodo quiz. We're going to be focusing basically the next 2 days on intermolecular forces. I like to spend a lot of time, so I think it's an incredibly important concept. And then we'll be all set with this unit for Regents. Honors will add on a little bit more. All right.